what's up? I'm going to talk a little bit about alpha-beta unsaturated carbonyl compounds. We talked about them a little bit in class today, but I think they're a really great place to highlight a lot of neat stuff about organometallic compounds and nucleophilic addition, all sorts of stuff that we've been going over in class. So unsaturated carbonyl compounds are compounds that have a carbonyl functional group right here with the carbon and the oxygen double bond. And then they also have a carbon-carbon double bond that's separated from that carbonyl group by one sigma bond right here. So hopefully you can see all that. This is your carbonyl group. Let me get a different color right here. And then this is your carbon-carbon double bond separated by one sigma bond. So and then the alpha beta refers to the different carbons of the carbon-carbon double bond. The alpha carbon is the one closest to the carbonyl carbon, and the beta one is the other carbon, or the carbon farther away. The neat thing about these compounds is that because of these resonance structures that I drew right here, you actually end up getting two partially positive carbons, the way that the electron density is spread out. And so let me see if I can highlight it here. The carbonyl carbon is partially positive, but the beta carbon right here is also partially positive. And so typically a nucleophile that has that is electron rich, maybe partially negative or even fully negatively charged, that craves that positive charge from a nucleus. It's a nucleophile. It likes the positive aspect of a nucleus. Would go after the partially positive charge of the carbonyl group right there. And typically, a double bond that's electron rich would be really attractive to an electrophile that's partially positive charge and seeks out the negative charge that a carbon-carbon double bond has heavily. Sorry, I'm not wording that right, but anyway, with these unsaturated carbonyl compounds, the carbon-carbon double bond actually has a partially positive charge, so it's also attractive to nucleophiles, and that means that nucleophiles can attack this compound in two spots, the carbonyl group or the beta carbon. And so it creates a 1,2 addition and a 1,4 addition. And before I go any further, let me emphasize which carbons I'm counting here. This is the, we'll say that this is the one carbon right here. Actually, I'm going to try to stay consistent here. I'm going to say the oxygen is number 1, the carbon is number 2, the alpha carbon right there is 3, and the beta carbon is 4. And so with a 1,2 addition, let me scroll down, you would have this unsaturated carbonyl group, and you'd have a nucleophile come in here. I mean, you got this partially positive charge and this partially positive charge, and the nucleophile can come and it can attack that the carbonyl carbon, forcing these electrons up, and so it'll give you one of these numbers. One of these electron lone pairs got pushed up as the carbonyl attached. And because you don't have a good leaving group here, eventually during your aqueous workup, water comes along, and the oxalate ion, this oxygen with the negative charge, abstracts a hydrogen, and you end up with a product that we're pretty familiar with by now. You know, it's the same method that Grignard reagents have used, and even organolithiums, and so that's the 1,2 addition. Another possibility is the 1,4 addition. The 1,4 addition is also called conjugated, if you see that terminology. But you start with that unsaturated carbonyl group, and you've got this partially positive charge as well on this beta carbon. Remember that the beta one is the one farthest from the alpha, or from the carbonyl group. This is the alpha carbon. But you've got that nucleophile with a negative charge, and it attacks the partially positive charge of the beta carbon, and it kicks these electrons. It opens that. These electrons come down, and it creates a negative charge right here, so I'll draw that. Nucleophile. The extra pair of electrons came over to the alpha carbon, so you've got this negative charge. And then at this point, you've got a couple options. You can rearrange, and these negative charge, or these electrons can come right here and reform a double bond, pushing the electrons from the carbon-oxygen bond onto the oxygen. So that'll look a little something like this. And so you've got both of those options. I'm going to show you right now why this one is favored. At this point, you would protonate. Sorry, this has a negative charge up here. Up in this top example, you would protonate that negative charge with when you have your aqueous workup. And so you'd have that hydrogen right there. And then you'd have your nucleophile, and you'd have the double bond would be in the carbonyl group. In this example, you'd have that oxygen protonated by the water, and your double bond would be internal here, and then you'd have your nucleophile. And we know that internal double bonds are more stable in an alkene situation, but a carbonyl double bond is even more stable of these two. So this is going to be the preferred. The reason it gets that 1,4 name is actually from this example down here, and so that's a little bit confusing. But what it's saying is that it added 1. The nucleophile added to this carbon right here, and then 2, 3, 4. The atom, which happens to be oxygen in this spot, that's 4 spots away, was where the hydrogen added. So you had the nucleophile add to the 1 and the hydrogen add to the 4. But this one up top is the more stable one. So I think that's the reason why they call it conjugated as well, a conjugated addition, because it's not technically 1,4, but it is different than the 1,2 addition. This is what's known as the 1,4 addition. So a distinction that we'll make, and again, this is a nucleophilic addition here, and so some of the nucleophiles that we've been talking about are the carbon groups that we've been making via Grignard reagents and organolithiums and even organocuprates. Oh, I guess I got a Microsoft error report there for Excel. Sorry about that. But that comes into play here because there's a distinction we make between which nucleophilic compounds will go 1,2 and which will go 1,4, and that's what he highlighted on the group assignment. So in the case of 1,2, you're going to see organolithiums do this. So that's RLI, and you're also going to see Grignard reagents, and so that's RMGBr, and in each of these cases, the R is the nucleophile, and then the metallic portion comes off as the, I'll do this, like the metallic comes off as the positive aspect. So we've got the R is the negative, it's the nucleophile. And with organolithiums and Grignard reagents, you do a 1,2 addition. It's because they form really electronegative R groups, and this is the mechanism of preference, because the more partially positive charge is the carbonyl carbon. 1,4 conjugated addition, we're going to see that with organocuprates. So the R2CuLi, where R again is the nucleophile. With these, you know, the lithium is the positive aspect, and then the kind of looks like this, R, the cuprate is the negative, and so the R ends up getting that negative charge and adding nucleophilically, but it's less negative through this mechanism. And also, I talked to Dr. Allison a little bit about it after class, some molecular orbital theory, which we don't talk about, and he doesn't talk to his organic class either about a whole lot. Molecular orbital theory plays a part in this, but that's why organocuprates add to the less partially positive carbon, that beta carbon, and why they do that conjugated addition and ultimately open up the carbon-carbon double bond as opposed to the carbonyl carbon. So anyway, I'm going to emphasize that with the question he used in the group work really quick. This is C and D from the 418 group work. I drew these so that hopefully it would be a little bit more obvious, but in each instance you're starting with 3 pentene, 2 enone. So you've got pentene as the base, 2 enone. The ketone is on the 2 carbon, and the carbon double bond of the pentene starts at the 3 carbon. So that's what I've drawn in both of these instances. And then in C, you're reacting with something, and you can tell, but I drew this so that it would be a little more obvious, but if you just straight up draw 4-methyl-2-hexene 4-ol, you might have to stare at it a little bit before it really resembles your starting product, and you can see exactly what happened. But you can tell that this carbon group right here was added to the carbonyl carbon, and then the oxygen was eventually protonated. And so for this one, since it added 1,2, or it attacked the carbonyl, you can add this carbon group onto a Grignard reagent. So MgBr, and then the R group would be an ethyl group. There's 2 carbons there, so ethyl. Or it also looks like CH3, CH2, MgBr. And then in this example below, you've got 3 pentene 2-enone reacts with something to form 4-methyl-2-hexanone. I drew it like this so that you can see that this 1, 2, 3, 4, 5 5-member carbon chain was our original carbon chain, and then this doohickey up here added to it. And so it added to the beta carbon, which is the 1,4 or conjugated addition. And so a good reagent for that one might be like ET2 CuLi. So that's the organocuprate version of this, and the R group that you want in there is an ethyl group because you want to add 2 carbons. So anyway, I thought that was pretty cool, and so I figured I'd make a video on it. Hope you enjoy.